All right, it's your boy, Dr. Torres, coming at you with a hot new lecture on stress due to bending. Let's get into it. So, the objectives of this lecture are to use what's called the flexural formula to determine or compute the maximum stress and stress at any point within the cross section of the beam. We're going to define a term called the neutral axis. We're going to determine an appropriate design stress for use in designing beams. So we're actually going to choose specific types of materials in this lecture that would withstand a specific loading condition. We're going to find another term called a section modulus, depending on the cross section. And we'll select standard sections of the shapes for use of the beam, like I said, with selection of material. Okay, so this lecture focuses on stress again, but it's not stress just due to a direct applied load, like we saw in the second or third week of this class, where sigma is equal to F over A, where it's just a distributed force. This is if something is bending. Like as you can see in this picture, we had something that was suspended between two edges. There was two applied forces on it, and then it gets bent. Well, when it gets bent, it also is under stress. Okay, and when it's under stress, we need to figure that out and select an appropriate size or material to undergo that stress so that it doesn't fail. Okay, and then here's like a cross section of maybe this thing that was being bent here and here with some moment that's applied on it that would be bending. Well, when something's bent like this bottom surface is going to want to elongate because it's getting longer down here at the bottom. You notice like how this picture, the edge is getting beyond this little constraint? Well, in order for it to bend like this, the bottom edges are having to get longer. If they're having to get longer, they're under tension. Well, the converse is happening at the top up here. This line is now getting shorter than where it previously was when it's being bent. So on the top, all the top surface is under compression. It's getting squished. So when something's bending like this, it has both compression and tension happening at it at the same time. And notice here's this centroidal axis here, right in the middle. Okay, that's also referred to as the neutral axis. And since it's compressing on the top and tension on the bottom, well, in the middle, they cancel out and nothing is happening. There is zero force at the centroidal axis. That's why it's called the neutral axis. There's nothing happening there. There's no force on there. So designers use this principle to their advantage in knowing that there's no force happening right there. It's balancing out. So they might strategically place things there in the centroidal axis so that there's no force on it and it'll be okay. Doesn't always work out that way, but it's just we know that principle. Okay, so this is what we're focusing on. Well, there's a formula to apply this that I mentioned in class a couple weeks ago. Well, we still use sigma, okay, but the formula is a little different. It's m multiplied by y, and all of that is divided by I, okay? It's m multiplied by y, all that's divided by I, where sigma is the bending stress this time for these types of problems. M is the bending moment at the section of interest. Okay, so wherever you're trying to figure this out, you want to use M. If we're trying to figure out what the maximum bending stress is, then obviously you would use the maximum M. And this is determined from the shear and moment diagram. So unfortunately, if you didn't like that topic, you might still need to brush up on it because this is where this comes from. Sometimes it may be given to you, sometimes it's not. And it's also to be noted here that this is always the maximum absolute value. So if the biggest, you always choose the biggest number from the shear and moment diagram, particularly from the moment side, even if it's in the negative side. Okay, so if it goes into like positive 15, but it goes down to negative 35, well, the beam doesn't care whether it's tension or compression. That's just the maximum force it's going to feel. So you need to design to that maximum force that it's going to feel regardless of compression or tension or positive or negative moment. It doesn't care. It's just going to get that maximum force. So we need to design for whatever the maximum absolute value is. Then y is the distance from the centroid, remember where nothing is happening, to the fiber of interest. When I'm saying fiber, this is like a textbook term to refer to the outer or the position of interest of the beam along the cross section. It could, like, What I mean by position is like the top, the middle, this specific distance, 5 inches from the center or 15 inches from the center, a specific location. So think location right here. This is just a textbook saying that the fiber, which is a portion or position of the material. And then I, we just got done calculating and figuring out, is the moment of inertia of that cross section. So sorry if you hated that lecture, you need to brush up on that as well, because this lecture uses both of those principles. Okay, so as I was describing that general formula, well, the maximum one is, has a little max under here, and this is the one we typically use, and it's MC over I. Remember the torsion lecture where it was TC over J? Well, here the C is the exact same thing. And C is the distance from the centroidal axis of the beam to the outermost fiber. And again, when I'm saying fiber here, I'm saying the outermost position, like the furthest you could get while still being on the picture, on the beam or whatever the cross section is, from the centroid, okay, the outermost fiber. And then M, like I said previously, it's the maximum moment occurring on the beam. So if you're using this previous equation, as I go back, this is the general one, and it's for a specific location. Like if we want to know what the moment has a specific location, we'll pull the moment at that location, 5 feet into the beam. And then if we want to know where it is, just like 5 inches on the cross section, we'll use this one. So this is the one that's more specific, and this is the one that we'll typically use in this class. They're basically identical. The only thing that's changing is the location that you want to know where the moment, the maximum stress is at, C. Okay, so here it is visually. So just like the torque and the torsion lectures, where the maximum torsion was occurring at the outer edge, the fibers is what's referred to in this lecture, the maximum bending stress is also there. Here it is like plotted in picture form, just like I described in the second slide. Okay, the maximum is at the outer edge. This is what I mean by the fiber. This is what the textbooks mean by the fiber, the outer edge. Okay, the outer edge of this cross section. This is the beam going long ways, and this is the cross section. This is what it looks like if you turn it. Okay, and if it's in positive bending, where the load is pushing down on it and it sort of smiles at you, that's known as positive bending, then there'll be tension here on the bottom, and it will be maximum at the outer edge. Similarly, it'll be maximum compression up here at the outer edge. And look here, this one's defined as neutral axis in 0. It's happening right there, and they balance out. Okay, well, notice this works out for when the beam is symmetrical like this I shape. Okay, it's symmetrical about this point. Well, a T-shaped beam like this is not symmetrical, right? There's not this piece down here anymore. Well, the neutral axis moves up, and the neutral axis is where? Well, at the centroid. Okay, so again, if you hated that lecture, here it comes again. Centroid is also where there's no force. Designers will use this principle to their advantage and maybe put some conduit or put some lines there or do something with it, okay? But that's where stress is 0. Okay, notice that here the maximum tensile stress was the exact same value as the maximum compression stress. Down here in a non-symmetrical beam, the maximum tensile stress was significantly higher than the maximum compressive stress. Okay, so this is something to definitely consider, and this is the primary principle behind reinforced concrete. Concrete is great in compression. Concrete loves to get compressed. It's like, I'll take compression all day. But it sucks in tension. But you know what is good in tension? Steel. Steel doesn't give a crap about tension or compression. We're just like strong, and we're just going to take whatever direction. So, well, if you combine steel to concrete, but putting the steel in the heavy tension side, then you've created a reinforced concrete structure. And that's what all concrete in basically the world is also has steel in it to combat the tension forces. Okay, combine the superpowers to form one super material called reinforced concrete. Okay, but it's primarily only in the tension side because the concrete's like, hey man, I got it up here in the compression side. Okay, so this is the principle that we're trying to solve for. So we're going to use that equation, specifically the my over I equation for this cross section, this T cross section. Okay, it's shown in the figure. Okay, it's a simply supported beam. Okay, that's not shown, but just assume a pin and a roller, the horizontal line. It's carrying a bending moment. I've thankfully already solved for the shear moment diagram, and I'm going to give it to you as a 100,000 pound inch as the maximum moment that occurs due to whatever loading. It has been determined that I is 18.16 inches. Again, I've already given that to you. The centroid, nicely given to you, is 3.25 from the bottom right here. 3.25, you can see. Y bar is 3.25. What I want to determine is the stress due to bending in this beam at 6 axis, A to F. Okay, what does that mean? Well, I just want to know what it is at point A, this little edge right here, the bottom. B, 1 inch from the bottom. C, 2 inches, and so forth. D, E's over here, and F. I want to know what it is at every single position. That's why we're using my over I, because y is now just that distance. Okay, now I have it solved out over here. Okay, so here, it's the same problem I just printed out. Okay, we're using the sigma equals my divided by I equation. M is given in the problem as 100,000 pound inch. I is 18.16 inches. And y is just the distance from the centroid to the location of interest. Okay, from the centroid to the location of interest. I'm going to do A. Okay, so A is down here. M is 100,000 pound inch. The y is 3.25. Okay, the distance from here to A is just y bar, 3.25. Then I divide that by I, 18.16 inches, and I get 17,896.4 pounds per square inch. Okay, units work out. Inches is the fourth on the bottom. There's 2 inches squared up here. Those go away. 2 of them go away. It's pound over inches squared, which is PSI. Cool. So now let's just do it for B. Same equation. Everything's the same aside from Y. Y is now 3.25 minus 1 inches. The distance we care about is, here's B. We care about from the centroid C to B. Well, how do I get that? I subtract 1 from 3.25. I get 12,389.8 psi. C, the same thing. Y changes. Now it's 3.25 minus 2. Okay, because point C is right here. 3.25 minus 2, we need this distance. Okay, D, everything's the same, but it's 3.25 minus 3.25. Well, that's going to be a big fat 0. Everything else goes away, and that's 0. Well, just like I told you, the stress due to bending at the centroid is 0. That's the neutral axis. Cool, right? So, sigma E at point E. Point E is right up here, right on the edge of what's called a flange in these types of beams. So, the flange right here at the interface. Well, that is 4 inches minus 3.25 now. Now the distance is from here to here. Well, how did I get the 4 inches? Well, 4 inches is this total distance from the bottom. Minus this 3.25 gives me the remaining little distance right here. Okay, that equals 4,129.9 psi. F is the last distance, which is the outer fiber up here on the edge. Okay, 2 outer fibers, this one and this one. Okay, if you really don't like that word for this, the outer edge. A here, point A and F. So we're doing the other outer edge, F. Okay, which the distance from C is just here to here. Okay, which is going to be the 5 inches minus 3.25. Okay, that's what I have. 5 inches minus 3.25. Everything else is the same. I get 9,636.6 psi. That's it. That's how we do it. We just have an equation. We just plug stuff in when we ensure proper units. Make sure we plug the right stuff in. That's it. Okay, then I go back to this lecture. Okay, this is the same problem, but with just the values plotted. Okay, so up here at F, it's 9,637. They did some rounding from the numbers that we have. They try to make the numbers like nice and more whole numbers, but the same process. But it's just, here's all the values, how it changes. Okay, and A was the maximum. Look, 17,000 versus 0 at D, and then started to rise up here in tension, but it only got up to 9,600 something. Okay, these are all the stresses and PSI. Okay, the next topic is section modulus. This is basically a direct measurement of the material's strength. Okay, there were some questions in class about I and J and what does that represent. That's its resistance to bending and torque, or bending uh, due to moment. Okay, but there's another number that kind of could represent its strength, and that's called a section modulus. And just higher numbers mean it's generally stronger. The way to calculate it is just I of the material divided by C of the material. That gets us a section modulus. These are all like found in textbooks based or design manuals where you have like known shapes that companies already knowingly manufacture. Well, they can just calculate this, right? I is just based off of some numbers. C is based off of some numbers, and you can just divide those and get a section modulus, and that represents that information. You could use this to determine what like a maximum stress would be. So you would divide the section modulus into whatever the maximum moment is, and that would give you the maximum stress that this material could ultimately hold, theoretically. Okay, within that, there's this table that's going to be real important for the next set of problems that we're going to solve. Okay, these are some design considerations. Remember, one of the objectives of this lecture is to eventually take this maximum stress concept and then be able to use it to select or design specific materials that would withstand the loading conditions that produces this stress, or specific like height or dimensions of a material that would be able to resist the specific types of stress. Okay, well, one of the tables a designer would use is this. Okay, notice this first column is the manner of loading. How is it being loaded? Almost everything in this class we talked about so far is statically loaded. The load is just there and it's sitting there and it does nothing else. It just sits there and it does to the material whatever it's going to do to the material. Well, what if you just constantly repeat it? There's other types. The second one, okay, what if I just like repeat the load? I just add 100 pounds, I take it off. I add 100 pounds, I take it off. And I had, okay, it's like the material's like working out, right? Or whatever, right? So it just constantly has that. The last one is an impact or shock. Like, what if you drop something on it? Okay, this is like the scenario about like dropping your phone and how the phone case and the screen resist the impact or shock. Okay, it's just one time, and that's it. Well, based off of those different types, there's two different materials in the world. There's a ductile material and a brittle material. Okay, the ductile materials are the ones that are going to stretch. You could see them stretch before they break. Brittle materials, like you have really no clue, and it just breaks and it's just sudden. Okay, like glass could just break. You might see some cracking and stuff like that, but it's not getting longer or stretching like that. It just breaks, right? There might be some information that might give you that's going to break, but ductile materials, you can see them start to stretch, like taffy or gum or whatever. Steel is the primary one, a good example of a ductile material, where concrete's more of a brittle material. But amongst those, all of these sigmas with the D is sigma design. Okay, sigma design. Okay, then SY is the sigma yield. Remember when we talked about the stress strain diagram in the class, and the yield is when a material is going to start to permanently deform. Okay, just like if you take a paperclip and you bend it, well, and it doesn't go back, well, you've permanently deformed it. You've gone past its yield point. Okay. This is the only one that has yield. All the other ones are SU, which are ultimate. Okay, ultimate is the maximum amount of stress that a material can take. That's the maximum, and then it's real close to failure. It's still going to take a little bit more, but it's going to start deforming and ultimately fail. Okay, so it's the ultimate. So based off of those, a designer, depending on the type of material and depending on the type of loadings happen, a designer is only going to want to design the stress up to only like half of what the ultimate yield strength of the materials. Okay, we know certain material is going to start to yield at say 50 ksi. Well, do you want it to load to 50 ksi or more? Well, no, it's going to start to fail and people could die. So designers choose a number that gets it so it's never going to get that close. Okay, which they're going to only design to up to maybe half. Okay, or if it's a repeated load, okay, that's a more of an unknown. You design only up to like an eighth. Well, if it's an impact or shock, you only design the ultimate only up to 12. Okay, and similarly over here, if it's a brittle material, you only want to design up to a sixth of that value, a tenth of that value, or a 15th of that value. Okay, so this is how designers do that. They use these factors, these kind of like safety factors. So you're only designing up to half, so that if for some instance maybe it actually starts getting loaded more than it's anticipated, it's still going to be good. Okay, that's the premise behind this. Okay, so we're going to do a couple of test your knowledge where we're going to sort of use this table and use some information. Okay, so I know this problem has a whole bunch of stuff on it, but let's just walk through it quickly. So there's a beam. Okay, here's the beam. Here's the photo of the beam. Don't worry about the other stuff. Okay, it's made from ASTM A36. Okay, if you don't know what this acronym is, just know that that's just a designation for what type of steel it is. Okay, ASTM A36. It's a structural steel plate. Okay, it's to be designed to carry a static load. Okay, shown on the finger, just like this. 1,275 pounds here, 1,275 pounds here. The cross-section of the beam will be rectangular, with its long dimension vertical and having a thickness of 1.25. Okay, so here's the cross-section. Okay, its long dimension is vertical, this one. Okay, its base is 1.25. What I want to know is how high should we make it? Okay, so it's like a design problem now. Like, this is what a designer would face. Like, okay, the producers of this material, they might have a whole bunch of like materials that have a base of 1.25 inches, but they have like 5 different versions. They go like 5 feet, 5 inches, 6 inches, 7 inches, 12 inches. And they're like, okay, well, which one do you want? Well, a designer will then figure that out. Okay, that's the basis of this problem. We're going to use the information here. We're going to use the shear moment diagram that I gave you. And then we're going to use that table I just talked about to determine the proper height. Okay, and I have this right here. Okay, wait, here it is. Here it is. Okay, it's the same problem, it's just on a different looking like paper. So here's the cross section. Here's what the beam looks like. Here's the shear moment diagram, and it says the same stuff up here. So from the table, what table I'm referring to is this one right here. From the table, we know it's a static load. So I go down. Okay, static load. Okay. It's steel, and I just said that steel is a ductile material. So from the table, I'm plugging this little equation out. Sigma D equals SY over 2. Okay, so I've just written down the design stress is equal to the yield strength divided by 2. Okay, whatever the material is that's divided by 2 is going to be what we're going to design it for. Okay, well, it's a steel. I don't know what the yield strength of A36 steel is. Okay, so from table A12, what the heck is A12? That's also in the notes. I believe it's this next slide. Okay, A12. Here's a whole bunch of different types of materials. A36 carbon steel, conveniently first one, but there's A50 cold form steel, all kinds of other stuff. Okay, but here's all their ultimate strengths and yield strengths. Well, A36 carbon steel is what we want. Okay, its ultimate strength is 58 KSI. But its yield strength is what we want. That's 36 KSI. By the way, how do you think it got its name? A36. Pretty interesting, right? Okay, so we pluck that from the table. A36 steel has a yield strength of 36 KSI. Okay, remember it's KSI, 1,000 pounds per square inch. Okay, so therefore, sigma D, our design stress, is equal to 36 KSI over 2. I just plugged this SY in. So we're going to design something that needs to be at least 18,000 KSI for its bending stress. Okay, well, I know the bending stress formula for the maximum bending stress is just MC over I. C, I can figure that out. Well, H, we don't know what H is. So I'm going to leave C in terms of H right now, whatever it is. Whether it's 12, 24, 5,000 miles, whatever it is, C is always going to just divide that by 2. Okay, so it's just H over 2 right now. I'm leaving it in terms of H because that's what I want to solve for. I, for a rectangle, is always base height cubed over 12. I know the base. The base is 1.25 inches. Well, I can just leave this in terms of H as well. Whatever that H is, 2 inches, 4 inches, 5,000 miles, whatever, it needs to get cubed. And then that needs to get divided by 12. Well, if I'm just going to leave this terms in H, well, I can divide the 12 into 1.25 and make it a little nicer. And it's 0.104 height cubed. So I have C in terms of H, and I have I in terms of H. M is from the shear moment diagram of 45,900 pound inches. Okay, I just got this right here. The maximum maximum absolute value on this graph is 45,900 pound inches. Cool. Well, I'm going to put that in kip inch, 45.9 kip inch, because this is in kips. Okay, so I'm going to have consistent units. Okay, we already decided that this sigma, this regular sigma, could be also equal to sigma d. That's what we're going for, which equals 18 ksi. So then 18 ksi is equal to 45.9 kip inch, the m. C is h over 2. I is 0.0104 h cubed. Just solve for h now instead of sigma like we normally would do. Okay, so I'm just doing some math here. So the h over 2, I can put the 2 into the 45.9 and get 22.6. And then what happened to the h? Well, there's one h up here, 3 h's over here. That one takes one away, so now there's only 2 h's down here. Okay, then I'm going to take this denominator and multiply it by both sides, so it comes over here. So 0.104 times 18 becomes 1.872 h squared. Well, that's equal to 22.6. Well, then now I could divide 1.872 into 22.6 and get h squared is equal to 12.07. Take the square root of both sides, and I get h is equal to 3.47 inches. Okay, that's the minimum that we need for its height in order to meet a design stress of 18 ksi. Well, the manufacturers are probably not going to manufacture to 0.47. That's a little odd. They have the base into 1.25 inches and quarter of an inch. So let's probably specify something that's like in quarter of an inch increments. The closest quarter of an inch increment to 3.47 is just rounding this to 3.5 inches. So that's the answer to Test Your Knowledge Part 1. Okay, then back to the lecture. There's another Test Your Knowledge. Okay, which there's a beam. It's simply supported. There's some reaction here, reaction here. The cross section of this time is now a circle. Okay, it's a cylinder. Okay, it's used for a conveyor system for some production line that carries the load shown in the figure. Okay, supports are at A and C. This 20 kilonewton load at B and the 10 kilonewton load at D are to be applied repeatedly. Okay, this is like a realistic case in like some sort of production line in some sort of factory where stuff might be like falling and hitting here and falling and hitting here. Think of any of those like how it's made documentaries or movies you saw where stuff is falling on the conveyor belt and just moving along and moving along. Well, you need to know if that conveyor belt could withstand whatever is falling. So it's repeatedly many thousands of times to produce the load. Okay, it has been proposed to use a 50 millimeter diameter circular steel bar for the beam. Well, I want to know a suitable steel for the beam. Okay, can it be made out of aluminum foil, or can it be made out of A36 steel, or does it need to be something higher such that it doesn't fail? Okay, let's go to my notes over here. Again, here's the same problem on a different page. Okay, here's the beam. Okay, unlike the problem before, the shear moment diagram was not given to you. So that is the first step. Well, the first step in making a shear moment diagram is to determine the reactions at A and C. Well, just some moments at A, set that equal to 0, negative 20 kilonewtons times 0.2 meters, plus RC times 0.4 millimeters, minus 10 kilonewtons times 0.6 meters. RC equals 25 kilonewtons. Some forces in the Y, unknown RA minus the 20 kilonewtons plus the 25 minus 10 kilonewtons gets RA to be 5 kilonewtons. I've drawn those in here in red. Then I've gone ahead and produced the moment diagram. Let's focus on this first, not all the math everywhere else. So I've drawn the line vertically downward at every load. I have labeled that this is the shear line. It is 0. Kilonewtons is my unit, so I don't have to write that every single time. This is the moment 0 line, and the moment is in kilonewton meters. Units also written, so I don't have to write that every single time. Okay. A vertical concentrated load upwards causes a jump in the shear moment diagram to go to 5. It's constant in between point loads. I hit a 20 kilonewton load that causes a downward jump down to negative 15. I got that by 20 minus 5. Constant in between point loads. I reach another point load of 25 that jumps up to 10, which I got that by 25 minus 15. Then it's constant in between point loads. and then I hit another point load of 10 kilonewtons. It goes downwards to 0. I got 0 by 10 minus 10. Okay, now the moment diagram also starts at 0, just like the shear diagram. I know that it's a vertical, it's a line going upwards positively because it's a positive moment diagram that's a square. The magnitude is determined by 5 kilonewtons times 0.2 meters, which is done right here. 5 kilonewtons times 0.2 meters equals 1 kilonewton meter. Okay, here I know that it needs to be a downward slope line because it's a negative square here. Well, to what magnitude? Well, I do the math down here. I was previously at 1 kilonewton meter plus negative 15 kilonewtons times 0.2 meters, which I got from the distance here. That gives me negative 2 kilonewton meters. So it's a downward slope line to negative 2. I do the same process. Okay, I know it's an upward slope line here because it's a positive shear. I take off where I left off, negative 2 plus 10 kilonewtons times 0.2, the distance. That equals 0, so it closes out, and we're good. So that's our shear moment diagram. Okay, now with that obtained, then we start doing some math here. Okay, so from the table, okay, what table? I'm referring to this one again. This one. Okay, the manner of loading based off the ductile material. We know that we're doing a repeated loading, and we're trying to figure out, I believe I asked for a steel, so that would be sigma D equals to 1/8 of the ultimate stress. Say 1/8 of the ultimate stress. So from the table, repeated load, it's steel, which is ductile. Sigma D equals, let's cut off here, SU divided by 8. Okay, so the material needs to have a design stress that is 8 times its ultimate strength of SU. Okay, I just have rewritten that formula. SU needs to be equal to 8 times the design. Okay, because this problem we're trying to figure out what type of steel. Okay, what type of steel do we need? That does it need? So based on all steels, all type of materials have a sigma U or SU and an SY. Well, the steel that we want to withstand this loading condition that's repeated needs to be 8 times whatever the design strength is. The design stress. So what is the design stress, the maximum design stress? That's still equal to MC over I. C is equal to half of the diameter. It's a 50 millimeter diameter. I put it in meters. 0.05 meters divided by 2 is equal to 0.025 meters. The moment of inertia. Okay, if we use the radius, it's pi r4 over 4. I plug the radius in. 0.025 divided by 4 is 3.07 times 10 to the negative 7. The units got cut off. It's meters to the 4th. And M, here like I stated in the slides, it's the maximum absolute value from this chart. So it's not 1 because that just goes up to the maximum positive 1. But remember, the beam doesn't care if it's negative or positive. It's going to feel it regardless. So you choose the 2. Okay, you just get rid of the negative. That's why it's absolute value. So the maximum M that happens regardless of positive or negative is 2 kilonewton meters. Okay, then I can plug that into the MC over I equation. 2 kilonewton meters times C is 0.025 meters divided by the I, which I just got up 3.07 times 10 to the negative 7, equals 162,974.6. Okay, this is kilopascals because I left this in kilonewtons. Okay, kilonewtons divided by meters squared is a kilopascal. So then I wrote that as a megapascal, which got cut up. You just see the M here. So that's 162.9 megapascals is the design stress here due to bending. Well, remember, we need to select an ultimate strength that is 8 times that. So 8 times 162.9 megapascals is 1,303.2 megapascals. Okay, so I'm not rewriting this as 1.3 gigapascals because megapascals and KSI are the 2 common stresses written in these types of tables. So if it goes beyond a megapascal into thousands of megapascals, they usually still keep it megapascals so that every single number on the chart is megapascals, and none of them, like the ones that go into the thousands, don't change to gigapascals. So I go to table A10 and choose this type of steel that has a ultimate stress, SU, that is slightly higher than 1303. Okay, you don't want to choose anything, just anything that's higher than this, because something that has 5,000 megapascals is definitely going to work. But something that has 5,000 megapascals as its ultimate stress is going to be big and bulky. And big and bulky means bigger, or means more material. More material means more money. So a designer needs to pick something that is just a little bit bigger than this. Maybe like 1,400, maybe even 1,320, something that's just bigger than that, because we know it meets the design conditions, and we know it's going to be the cheapest for our owner, for whoever we're going to work for. So something that's slightly bigger than that. Well, table A10 is in your notes. I believe it's the last. Here's A12. Here's A10. Okay, this is what I was talking about. These are all different types of steels. Okay, these have all these designations here. Have some sort of condition as how it was like quenched or whatever. And then here's the ultimate strengths and yield strengths. And just like I said, they're always just written in KSI or megapascals. So there's stuff that goes into the thousands. So those aren't rewritten as 1.3 gigapascals, because people would get confused. Okay, so, and like I always said and stressed in this class, right, Pascal is only acceptable unit for stress. Okay, so Newton per millimeter squared are not in this table. So that's why I said at the beginning that it doesn't sound good. So only megapascals are written in here. Okay, so we're looking for something that's slightly bigger than 1303. Well, these are all smaller than that. Okay, this one's exactly at 1303. And it technically shouldn't work because our answer is 1303.2. And so 1303 technically isn't bigger than that. So, but it's only 2/10, and it's probably going to be okay. This might be a discussion with like the owner or maybe with someone to see if this would be okay. But it might be okay. We're designing for 8 times that. So it'd probably be okay, but if you're not comfortable with that, then choose something slightly bigger. And then there's 1331, 1350, 1351 down here. If you're really uncomfortable with that, then go with this one. So either one would work. I think in my notes, I said that the 1080 OQT70 is at 1303 megapascals. That's probably okay. It's 1303, so something equal to or slightly higher. This kind of depends on your style of designer. If you worry about that, then just pick the one that's slightly bigger, the 1331. Okay, that's it for the lecture. That's all to test your knowledge for this lecture. I'm going to break up the this video into the second part where I do the examples separately. So that's the end for this video for now.